So as CS people, what is your answer to that? Well, as yeah, mostly, partly CS people. And what's your answer to that?
Bootstrap.
Bootstrap, right? I can do some kind of simulations. The Bootstrap doesn't really give me sampling distributions per se, right? Yeah, Bootstrap is one way of doing it. Yeah, Bootstrap, you could do Bootstrap, but you have to be careful about it. So some kind of simulation based methods, right? Right, or I can do I can try to find the sampling distribution analytically, provided I have simple enough underlying data distributions and I know something about underlying distributions, then I can find the sampling distribution analytically. For example, so if I want to look at let's say let's take as a case where I am tossing coins, okay. So I toss a coin 20 times, okay, and end up with 14 heads, okay. So is the coin likely to be fair or not? Twenty coins, 14 heads, is it fair or not? We don't know. 20 coins, 18 heads. Okay, see, all of these are intuitive things. How will you make it? No, all of you know how to do this, right? Now tell me, how will you do it formally? Okay, you will set up a null hypothesis where you will say that the probability of the coin coming up heads is 0.5. That is a null hypothesis. The alternate hypothesis will be probability of the coin coming up heads is greater than 0.5. Okay. Now what I do is, okay, I run a sample which is 20 tosses. I found out that it is 14. So the statistics is 14, not x bar, it is not the average, but the statistics is 14. Right? This whole process can be done for anything, not just for mean, right? So the statistic is 14. Now I am assuming the null hypothesis is true, which is 0.5, okay, and I have to figure out what will be the distribution of the number of heads, right? So what is the probability that I will get one head when what's the probability I will get 0 heads if I toss 20 times? What is the probability I will get 1 head if I toss 20 times? What is the probability I will get 2 heads, blah blah blah, like that, right? I compute all the probabilities, right? Now I look at the probability of obtaining 14 according to this distribution, and if I do not like that probability, right, then I can say that no, it's reject the null hypothesis, right. If I like the probability, I can say no, accept the null hypothesis.
Should we compare the probabilities with null and alternate hypothesis?
There is no alternate here, alternate just says it is greater than 0.5, right. So in this case, yes, you can see, this is why you have to be very careful about formulating the alternate hypothesis, because at the end of the day I am going to say accept the alternate hypothesis, rejecting the null hypothesis. But if the alternate hypothesis was it is less than 0.5, that is not a valid alternate hypothesis to make given the data that you have, right. So it's nothing wrong with the whole hypothesis testing process itself, it's something wrong with the way you set up the problem, right. So if you aren't sure if it's higher or lower, then that is a different issue, then you can say not equal to 0.5 and then run the test, right. But then it's up to you, if you have to use your understanding of the domain to come up with appropriate alternate hypothesis. There is another question, yeah.
We first set the alternate hypothesis and then did the sample size, right?
Then
the sample, then the X bar mu we got. We first set up the alternate hypothesis, then we got the.
Yeah, that's not, I mean you do exploratory experiments, do you remember that? So I told you in the previous class, before you start your actual experiments, before you do your actual experiments, you do some exploratory analysis of the data, right. When you do the exploratory analysis, you will get some idea, okay, you will start suspecting that, okay, this coin is actually biased towards heads, and then only you will set up this experiment. So this is a very specific statistic that you gather while you are running the experiment, but before you set up the alternate hypothesis you should do some amount of exploration, right. So you can't walk into an experiment blind about the domain. So this is these are practical issues that you should be aware of. Remember last class I told you very much about the need for exploratory analysis, right. So you have to do exploratory analysis before you set up your actual experiment.
What is the confidence with which we can say that following these steps we arrive to correct answer?
Yeah, so that I will talk about. This is just the basic structure. I will talk about how about the confidence. That I will come to in a minute. Yeah. Right. So, but you know how to do this, right? You can analytically you can figure out what is the proportion of heads you will get in 20 tosses, right? So all of you know how to do the binomial, and then you can figure out what the probability is, right? So the another way of doing it, right? Just to give you another example of that, right? So another way is to make use of specific properties of the parameter that you are trying to estimate. In fact, if you are looking to estimate mean, right, so you have one big advantage. What is that? There is something called the central limit theorem. So what does the central limit theorem say? Right. So since the samples I draw are all independent samples, right? I draw samples of n variables. I mean size n, right? I draw samples of size n, and these are all drawn independently, right? I don't have any basis of any bias from the previous samples I have drawn. I am going to draw a lot of independent samples of n variables. So if you think about the performance of the algorithm on this, okay, it is essentially independent samples I am drawing from the same similarly distributed random variable, right. So essentially what central limit theorem tells us is, regardless of the underlying distribution from which the data is drawn, okay, the sampling distribution will be Gaussian, right, will be a normal distribution, right. It tells us that the sampling distribution will be a normal distribution, and anything else? Exactly. So the mean of the sampling distribution will be the mean of the population from which the samples are being drawn, right. So central limit theorem tells us that so I am going to call it the population mean as mu, right, and the standard deviation is right, where sigma is the population standard deviation. Right. So the thing to note is that this does not depend on the underlying distribution, right, regardless of what the population distribution is, right, the sampling distribution will be a Gaussian, the mean will be the same as the population mean, right, and the standard deviation will be sigma by root n, where sigma is the population standard deviation, right, standard deviation will be the population standard deviation by root n, right. So the larger the sample size, the narrower the sampling distribution, right. Does it make sense? So the sampling distribution will always be centered around the population mean, right. The one thing which you can control is how wide is the sampling distribution, right. So if n is small, then the sampling distribution is wide, when n is large, the sampling distribution is narrow, okay. So unfortunately we only have a central limit theorem for mean, right. So This is what I said, the sampling distribution of the mean. Okay. So I just want to stop once and just, I am sorry if it is getting too repetitive, just once more to emphasize what do you mean by sampling distribution of mean. What does it mean? Too many means. Reminds me of an old Kamala Hassan movie.
The distribution of the means, it's the distribution of the sample means of the data.
It's the distribution of the sample means of the data. So that's what I mean by sampling distribution of means. Okay, is that clear? Right, because I've seen people get confused and give all kinds of different interpretations of that. So I have the sample data. So I've taken I repeatedly sample data of size n from the population, right? And I compute the mean of these samples, and the distribution of that mean is the sampling distribution of means. Okay. Great. So this standard deviation of this sampling distribution is also sometimes called the standard error. It is called the standard error of the mean. Okay. The standard error of the mean is the standard deviation of the sampling distribution. Okay. So empirically, right, we can say that n greater than or equal to 30 indicates n is large enough, right, that your standard deviation, the standard error becomes small. Right. If the standard error becomes small, what happens? So any sample of size n I can take and estimate the statistic, and I am more or less correct, right, with a very high probability I will be correct. So that is what it means. But okay, you have to be careful about what is correct. So couple of caveats here. So if your population has a high standard deviation, so what do you have to do? You have to make your sample size very large so that your standard error comes down, right. But then if your variance of your thing is very high, the underlying population is very high, right, that means you will require very large samples, right. So what you should be thinking about at that point is to see if there is some other way you can set up the test, right. So you should not come to a point where I need millions of samples just to reduce my standard error. I am sorry? Yeah, that is what I am saying. You have to think of some other way of going about doing this rather than just saying that increase the number of samples, right. So what could be other ways of doing it is to try to bin data, right. So if you bin data, what happens is so small variations in the data will go away, right. So something like 3.2, 3.3, 3.4, 5, 6, all of them can be binned to say 3.5, right. That means the small variations will go away, so lesser amounts of noise, right. So the variance will also drop a bit. So you can do things like that, you can do some kind of noise reduction techniques, try to do see if you can reduce the variance in the data without actually dropping anything important. So that's crucial, right. So these are the kind of things you have to try. So that's one caveat that I wanted to say. So the next thing we will look at is specifically using the sampling distribution of mean, right, and come up with something called the Z test, right. So people know about the Z test, right. Okay. So again, okay, let's do another example here. Okay, so I am giving you know how to solve a certain kind of problem, right. So you have been trained to solve these problems for years and years and stuff like that, like you do in your JEE preparation kind of things, right. And then I know how much I would expect a student to score on a specific set of problems, right. Then suddenly I find that a new kind of problem comes up, right, and the students are taking longer to solve these problems, right. Let us say that the students takes a unit time to solve problems traditionally, now they are taking say 2.8 times that to solve the problems, right. So my claim is that these new problems are harder than usual, right. Okay, how will I verify that? Right, so again I am just going to walk you through setting up this hypothesis, right. So basically I am going to start off with saying that, so I have the easy problems, I have the hard problems, my null hypothesis is they are no different, okay. I am going to say they both take unit time to solve, right. So and the second is the alternate hypothesis is, right. So the easy problems take lesser time than the hard problems to solve, is it fine? So what I know from previous data is that just some numbers, right. The actual numbers are less important, but just the process here, right. And then so what, now I have set this up, I take 25 hard problems, I ask the students to solve it and I get my okay. So we are looking at mean, so the sampling distribution is going to be Gaussian, right. What will be the mean of the sampling distribution? Ah. You don't have to do that, yeah. Okay. So now what I am going to do is do a little trick. So I have the sampling distribution, right. So I need to know what is the probability of seeing 2.8 under this sampling distribution. So the mean is 1, the standard deviation is 0.19, right, and there is 2.8, I need to know, right, what is the probability of seeing 2.8 under this sampling distribution, right. So I can do that, and all of you know how to find the probability here, right. So this is mean is 1 and this is so many standard deviations above the mean, right. So the probability is actually very small, right. But we can also do this in a slightly more convenient fashion. So you basically find something called the Z score, which is essentially assuming that your sampling distribution is going to be 0 mean and unit variance. So what you do is this is called the standard normal, right. So standard Gaussian. So I am going to convert my sampling distribution into a standard Gaussian and then try to find the probability of 2.8 in that standard Gaussian, right. So essentially the Z score is So that will be the x score. So essentially I take my actual statistics, subtract the mean from that, right, and then divide by the variance. So this gives me the unit variance, that gives me the 0 mean, right. Sorry, this is, yes, the standard deviation, yeah, there you go. So it is 9.47. So essentially what it says is this guy is 9.47 standard deviations above my mean, right. So what is the probability of that happening? Very small, right. So what we do, well, we do not know that, so what we do is we essentially look at some standard values that we do know, right. What is the probability of something lying greater than 1.645 sigma above the mean? This numbers you should by heart, right? You should know it at some point. 1.65, 1.65 is your friend, right? So implies the probability of that happening is yeah. So basically what it means is, right, so this side is 95%, right. So if you take the Gaussian, take this is mean, right, take 1.65 sigma above the Gaussian, right, the area to the curve to the right of that is 5% of the total area, right. Likewise right, area here is 5%, right. So any of the numbers we need to know? Right. So why are we interested in 0.025? Two tail, right. Sometimes we might want to not look at greater than, we might want to look at not equal to, right. Now I have made my hypothesis was the second set of problems was harder than the first set of problems. If my hypothesis had been, if the second set of problems are different from the first set of problems, then I should have had mu is not equal to mu old, right. So in such cases I should have been looking at 0.196 because I could go on either side, right. So I have to make sure that my statistics is greater than either plus 0.196 or lesser than minus 0.196 for me to be sure that I will be wrong only 5% of the times, right. So in the olden days we actually used to have a Z table that used to tell you for one sided tests what should be the Z statistic you should look at, for two sided tests what should be the Z statistics you should look at, and so on and so forth. If people have actually looked at Clark's tables ever, you actually have a Z table as part of the Clark's tables, and this is essentially what the Z table is telling you.
Mu is the population
Mu where?
mean. Mu E is the population mean.
Mu E is the easy task that we had, right? Yeah, that is under the null hypothesis, that is the population mean. Yeah,
So
right.
the actual answer is now the probability is less than 0.05.
Yeah, so now it's 9.47, right? I mean 9.47 is way higher than my 1.65, right? So therefore I can reject the null hypothesis, right, at a confidence level. The way we stated is like this: I can reject the null hypothesis at a confidence level of at least 0.05. So that means that the probability of me making an error in rejecting the null hypothesis is less than 0.05.
So the actual thing is now the paper is actually harder.
Exactly harder, yeah, it's actually harder, yeah. So that the conclusion is that yes, it is harder. So I accepted the alternate hypothesis, right, so rejecting the null hypothesis, and the probability of me making an error is less than 0.05. Okay, does that make sense?
So in that case, would the confidence level be like 95% or?
Yeah, you could say that, but confidence levels mean something else. Okay, so that's why the statisticians are very careful about the conclusion that they will draw from this. I will write down the conclusion. Okay, you can say p level or a p value, right, but it's essentially the p value of something means the probability of you being wrong in that conclusion. Okay, so probability of me being wrong in this conclusion given all the assumptions I made. See, this is the reason why we want a very high things, right. We are assuming our sample size is large enough for central limit theorem to apply, right, and so a whole bunch of things that we are doing, right. I'm sorry.
Your 95% confidence that H1 is correct, right? Your 95% accuracy.
There's no that's the point here, right. There is no notion of accuracy here. So the probability of me making an error in concluding that H naught is not right is 5%. Okay.
Right like this, or can you just say the probability is 95?
So if you want the whole nuances of saying confidence is 95%, I recommend you to read the book. So it's not, you cannot really say confidence is 95%, right. So I can just say the probability of error is this. I'll come back later and tell you when you can say confidence, when you talk about confidence intervals, right. At this point I will just leave it at this, right. Right, therefore we can reject the null hypothesis. So this is good, right. This is the Z test, yeah.
In that sigma x bar calculation, shouldn't we be using the sigma of the hard problems instead of the sigma of the easy problems?
Under the null hypothesis they are the same, aren't they? Right, that's the whole idea, right. Under the null hypothesis, what is the sampling distribution? That's what we are trying to, under the null hypothesis being true, what is the sampling distribution is what we are trying to find, right. So they are the same then, the null hypothesis is true. Right. So typical p values that you run these things are at so if you are looking at more critical domains like medical domains and stuff like that, I would expect a p value of 0.001, right, not 0.005 even. Okay, so you have to be more careful, really sure about what kind of